Welcome to these NPTEL lectures on dynamics and control of mechanical systems. In the last week, we had looked at the properties of a body in terms of mass, its distribution of mass, also the inertia matrix, and we had looked at the linear and angular momentum and the various types of external forces which act on a rigid body or a multi-body systems. In this lecture, we will look at the equations of motion of a rigid body. My name is Ashitava Ghoshal. I am a professor in the Department of Mechanical Engineering and in the Center for Product Design and Manufacturing, and also in the Robert Buss Center for Cyber Physical Systems, Indian Institute of Science, Bangalore. On the topic of equations of motion for a rigid body and multi-body systems, there will be 5 lectures. These will be spread over the next 2 weeks, this week and the next week. In the first lecture, we'll look at introduction and a recap of the contents which we have done before. In the second lecture, we'll look at the Newton-Euler formulation for serial chains. This is a very well-known approach which is used extensively in many robots and other mechanical systems. In the third lecture, we will look at what is called as the Lagrangian formulation, and this is also a very well-known approach to derive equations of motion for rigid bodies and multi-body systems. In lecture 4, we will look at examples of equations of motion which we have derived, and I will show you the steps required to derive the equations of motion. And finally, in lecture 5, we will look at how these equations of motion could be obtained using computer tools. Lecture 1, Introduction and Recap. In this lecture, we will quickly overview this whole area. The first important thing is, till now in kinematics, the cause of the motion was not considered. In dynamics, the motion of a rigid body or a multi-body system due to external forces and or moments are considered. Okay, so that is the topic of dynamics. The main assumptions in this whole set of lectures and in this course, in fact, is that the rigid bodies are used. There is no deformation in the body or in the link or whatever is making up the mechanical system. The motion of the rigid body is described by ordinary differential equations, also called equations of motion. So if you have a rigid body, we will naturally get ordinary differential equations. If you have deformations in the rigid body, we do not get ordinary differential equations of motion. We will have partial differential equations. So we will not worry about partial differential equations. We will only limit our scope to rigid bodies which naturally give only ordinary differential equations. There are several methods to derive the equation of motion of a rigid body or a multi-body system. These are the 3 main ones. One is called as a Newton-Euler, one is called Lagrangian, and one is called Keynes method. In the Newton-Euler approach, we obtain the linear and angular velocities and acceleration of rigid bodies. We draw free body diagrams, and then we apply Newton's law and Euler equations to each of the free body, and then we do a lot of simplification to arrive at the equations of motion. In the Lagrangian formulation, we obtain the kinetic and potential energy of each rigid body. We obtain a scalar quantity called the Lagrangian of the system, and then we take partial and ordinary derivatives. Okay, so this is an energy based approach, whereas in the Newton-Euler we have to obtain velocities and acceleration. In the Lagrangian formulation, we can get away with only obtaining up to velocities. In the Keynes formula, we choose what are called as generalized coordinates and speeds. We obtain generalized active and inertia forces and equate the active and inertia forces to obtain the equations of motion. We will not be looking at this in this course. Okay, anybody who is interested can search Kane, and then there is a lot of material available on how to use Kane's formulation to obtain equations of motion. Each formulation has its own advantages and disadvantages. So we will look at Newton, Euler and Lagrangian formulation, their advantages and disadvantages. But as I said, we will not study Kane's formulation in this course. So let us continue. This is it. To recap, we have something called the mass and inertia of a rigid body. So this figure shows a rigid body. Okay, so there are rigid body, and we have an associated coordinate system xa, ya, za with an origin OA, and we look at a volume element dV, and let's say the volume element is located by this vector AR. So we can find the center of mass of a rigid body by performing this operation, which is the location of the center of mass is given by the volume integral of AR rho dV divided by volume integral of rho dV. So the volume integral of rho dV is the mass, it's the total mass of the rigid body. And this vector locates the center of mass as shown here in this figure. We also have something called the inertia of a rigid body. This is basically the distribution of mass about these three axes x, y and z, and we had looked at this in the last week. So we have something called as an inertia matrix, okay, and this is nothing but the volume integral of rho dV but multiplied by a skew symmetric matrix AR square, okay, and AR, remember, is some kind of a vector xyz but written in a skew symmetric form, okay, of a matrix. So, and this inertia matrix is with respect to a coordinate system, in this case A, and it is about a point. So we need to mention the inertia matrix of a rigid body is with respect to which coordinate system and about which point. So in this, it is shown that it is with respect to the A coordinate system, and it is about this origin of the A coordinate system OA. So as I said, this skew symmetric matrix AR, if you multiply minus AR into AR, so it's square of the skew symmetric matrix, you will get terms like y square plus z square, x square plus z square, x square plus y square along the diagonals, and the off diagonal terms will be minus xy minus yx. So it is still a symmetric matrix, okay, and based on this skew symmetric matrix AR and the square of the skew symmetric matrix and the volume integral, we can define elements of the inertia matrix, which are Ixx, which is y squared plus z squared volume integral into rho dV volume integral. Ixy is minus xy rho dV, again volume integral. Xz is minus volume integral x into z rho dV. So you can see that the subscript x and z, and here also we have x and z. So likewise yz is volume integral yz rho dV. The diagonal terms ixx, iyy and izz, they are square. So it is y square plus z square here. In iyy we have x square plus z square, and in izz we have x square plus y square. Okay, so this is the 3 by 3 matrix. The inertia matrix is symmetric and positive definite, and as a result the eigenvalues of this matrix AI are real and positive. So we have 3 eigenvalues which are also called the principal moments of inertia, and the associate eigenvectors are the principal axis for the rigid body. Inertia is often computed or available with respect to the center of mass, and this is available in many textbooks and some mechanics textbooks, and at the end of the appendix. We can obtain the inertia matrix with respect to some other point and about some other coordinate system by using the transformation of the inertia matrix. There are 2 of them which are possible. One is rotation or by parallel axis theorem. Parallel axis theorem is translation from the CG to another point. And rotation is at the CG. If we have two coordinate systems A and B, we can relate the inertia matrix in the A coordinate system and in the B coordinate system by multiplying by the rotation matrix ABR. So let's continue. So a very important notion or use of or to obtain the equations of motion is Newton's law. So let us briefly recapitulate what is Newton's law. So basically we have a rigid body, and let's say there are these external forces AF1, AF2 and so on, which are acting in this rigid body at these different points. So AF1 is acting at AR1, AF2 is acting at some other point and so on. Okay, and what are these AF1, AF2? They are the external forces. Last week we had looked at different kinds of external forces, say gravity, spring, damping and so on. So if you have a rigid body subjected to these n external forces which are acting at n points on the rigid body, we can obtain an equivalent description of all these forces on this rigid body as that there is a resultant force AF and there is a resultant moment which is acting about the CG, or the center of mass. Okay. So these two pictures are equivalent. Instead of having n forces, we can have a single force and a single moment about the center of mass. The linear momentum of this rigid body can be obtained as volume integral of AR dot rho dV. What is AR dot? It is the velocity of the center of mass or velocity of some other point. Most of the time we will use center of mass. The linear momentum of a particle of mass m at the center of mass is given by m into velocity of the center of mass. So velocity of the center of mass with respect to the A is denoted by AVC, and it is the linear velocity of the center of mass in the A coordinate system. Okay, and this is C is the center of mass. Newton's law states that the sum of all these external forces AFI, or which is the same as this AF, is nothing but time derivative of m into AVC. So remember, AVC, m into AVC is the linear momentum. So Newton's law says that this resultant force is equal to mass times time derivative of the linear momentum. For constant mass, okay, we can take this m outside this derivative, and what we have is the force is equal to m times acceleration. Okay, this is very well known standard expression of Newton's law, that the force which is acting on a rigid body will result in an acceleration which is denoted by F equals ma. Okay, and what is this AC? It is the linear acceleration of the center of mass. One important thing to remember is Newton's law, this expression is valid for an inertial frame, meaning that this A coordinate system must be an inertial frame. And if you go back to your undergraduate or even physics, high school physics, there is no such thing as really as an inertial frame. Okay, so inertial frame is basically something which is in a simplistic way, which is not rotating. Okay, so what is an inertial frame? Now, a good approximation of an inertial frame is the lab, okay, or the surface of the earth. But we know that the earth is rotating, okay, it is spinning about its axis, so it is not strictly an inertial frame. So if you think that the center of the earth is an inertial frame, that also is not true, because the earth is going around the sun and so on. So although there is strictly no such thing as an inertial frame, but Newton's law is valid only for an inertial frame. Okay, and we have reasonably good approximation of inertial frame when we say that the lab or the floor of the lab is an inertial frame. So let's apply this Newton's law, and we'll take a very simple example. So what we have is a mass, which is connected to a fixed ground by means of a spring K, and also a damping element, which damping is given by this C. Okay, remember, one way to measure the force exerted by a damping element is something like Cx dot. So the mass is at a distance x and it is accelerating to the right by x double dot. So Newton's law says that the sum of all these forces is equal to m times a. So what is a? It is mx double dot. And what are the forces which are acting on this mass? So what you can see is there is a k times x which is going in the opposite direction to x dot, and there is a cx dot. So what we have is mx double dot is equal to minus kx minus cx dot. Okay, and this we can rewrite it as mx double dot plus cx dot plus kx equal to 0. It is also possible that there is somebody pulling this mass. So maybe there is some string attached and you are pulling it, or maybe there is an external force of some kind which is acting on this mass, and let's denote this external force by f of t. It could be time varying. Okay, so then the equation of motion of this mass is mx double dot plus cx dot plus kx is equal to f of t. Okay, this is a very standard equation which is used in vibration, and everyone must have seen this. And so basically what we are doing is we are applying Newton's law, which is sum of all forces is equal to ma, and we get this equation. We can also look at what is something called as an Euler's equation. Okay, to look at Euler's equation, we again go back to this picture of a rigid body. We have a volume element rho dV, which is located at a point A, P. Okay, the center of mass of this rigid body is located at this point and is located by this vector ARC. And from the center of mass to this volume element, it is AR. Okay, and all of these are with respect to a reference or a fixed coordinate system XA, YA, ZA with origin OA. So the angular momentum of this rigid body is defined as this AP cross AP dot rho dV. So what is AP dot? That is the velocity of this volume element. Okay, and then we take the cross product of this velocity vector. So the velocity vector will be in some direction with this AP. So it is like R cross MV. Okay, so this is like M, this is like V, so this is R cross MV. And again we integrate over this volume element, and just like other vectors, okay, we need to define this angular momentum with respect to which point. In this case it is with respect to OA, and which coordinate system. In this case it is with respect to the A coordinate system. Okay, so now as you can see, there is a cross product involved, and we can write this cross product as a skew symmetric matrix AP into the rest of it, which is AP dot rho dV. So instead of writing R cross MV, we can write a skew symmetric matrix into MV. Okay, as a in this form. This is perfectly reasonable. It helps later on, we'll see when we write it in this form. So the angular momentum about the center of mass instead of about OA can be written as AHC. Again, A means reference coordinate system A, and C means about the center of mass. Is again, we can write this vector as AR cross ARC dot plus AR dot, because AP dot can be written as the derivative of ARC dot plus AR dot. Okay, so this AP dot is written in this form, and then if you integrate, you can show that the volume integral of this skew symmetric matrix AR into ARC dot is given by minus ARC, because it's a cross product of two vectors, and you can change the order. So like A cross B we can write as minus B cross A. So we can take out this ARC dot with a minus sign, and then we are left with a volume integral of AR rho dV. Okay, so now this AR rho dV is 0 because that is the definition of center of mass. So as you can see, using this nice way of using a cross product as a skew symmetric matrix, we can show that this part of the term AR into ARC dot is 0. So this AR into ARC dot is 0. So we are left with only one more term. Okay. So what is AR dot, which is this part here? This AR dot is nothing but omega cross R. And of course, we have to be very careful when we are taking cross product, and also the which omega we are interested in. In this case, we are interested in the space fixed omega, which is R dot R transpose. So AR dot is nothing but omega cross R, and which is, remember, the space fixed angular velocity vector can be written in terms of a skew symmetric matrix A B omega R into R. Okay. So again, instead of writing omega cross R, we can write minus R cross omega, because if you change the order of the cross product, we have to put a minus sign. And hence, we can write AHC as minus this AR is here. So we are rewriting AR dot as minus AR into A omega BS. Okay. And then AR into rho dV, and we can take out A omega BS outside. Okay. So what do we have? That the angular momentum about the center of mass of this rigid body is a volume integral which contains the square of these two skew symmetric matrix. Basically, it is like R square, where R is a vector, okay, from the center of mass to a volume element, and then into angular velocity. So what do we do with this angular velocity? We can rewrite this angular momentum and angular velocity as AHC, just from the previous slide, can be written in terms of the inertia matrix. So if you go back and see the definition of the inertia matrix, this AR skew symmetric matrix square into rho dV and volume integral with a minus sign is the inertia matrix about the center of mass in the reference coordinate system A into A omega B. So the angular momentum is I into omega, which is what we have done seen in undergraduate. So if you take the derivative of this angular momentum, which is AHC, which is derivative of both of these, and then you can use the chain rule. So we can see that this derivative AIC into A omega, this can be written in two ways. One is we can go back to this A omega BS, and we can pre-multiply by a rotation matrix and get A omega B in the body fixed coordinate system. And then we also have AIC that can be converted to the body fixed as some ABR BIC into ABR transpose. Okay, so those of you who have, if you go back and see the notes, you can see that the inertia matrix in the B coordinate system and in the A coordinate system are related by R, I, R transpose. And that R transpose into this will give you the body fixed angular velocity vector. So this, whatever these two terms in the bracket, can be written as some rotation matrix into inertia matrix in the body coordinate system and body fixed angular velocity vector. Why are we doing this? Because this inertia matrix in the body coordinate system does not change with time. Okay, it is a number, it is a bunch of numbers only, it's constant. So when you take the derivative of this, we will get some R dot into this inertia matrix into A omega B, plus we have this R into IC, because the derivative of this term will be 0, into A omega B dot, derivative of the angular velocity. So this is like angular acceleration. The third term in the chain rule is derivative of BI, this one will be 0. Okay, so note B I dot C will be 0. So what do we have here? That the rate of change of angular momentum is given by this expression. Okay, so let's pre-multiply both left and right side by BAR. So again, we are basically converting it into another coordinate system. So if you pre-multiply AHC dot with BAR, we'll get some ABR transpose. Why ABR transpose? Because BAR is same as ABR transpose. This is the inverse of ABR, which is same as the transpose. And hence we have ABR transpose into ABR dot into some inertia matrix into body fixed angular velocity vector plus again ABR transpose into ABR into body fixed inertia matrix into A omega B dot. Okay, so this is like angular acceleration into some matrix. See, note that these two will become identity. So this is like R transpose into R. How about this? This is R transpose into R dot. Okay, so this is like again angular velocity, but the body fixed angular velocity. If you go back and see your notes, the space fixed angular velocity is R dot R transpose, whereas the body fixed angular velocity is R transpose R dot. So hence, the rate of change of the angular momentum in the B coordinate system can be written in terms of a skew symmetric matrix, which is A omega BL. So this is the left multiplication, or we'll see later it is the body fixed angular velocity vector into some inertia matrix into angular velocity plus this inertia matrix in the body coordinate system into A omega B dot, again the body fixed angular rate of change of the body fixed angular velocity vector. Okay, so what is this? This is like some kind of a skew symmetric matrix. This part is like a vector. It is like some matrix into a vector which will give you a vector, and this is like a skew symmetric matrix. So this is like some vector cross this. Okay, so this is a cross product of these two, this part and this part together, and this is some matrix into angular acceleration. So hence, in vector form, this above expression can be written as the rate of change of the angular velocity vector about angular momentum about the center of mass in the B coordinate system is something like BIC into A omega dot. This is from this part, and this part is A omega B cross I omega. Okay, so this is very well known. This is well known what Euler's equation. And what is the Euler's equation states that the rate of change of the angular momentum is equal to the net external moment acting on the rigid body. So this part from here, which is something like I alpha plus omega cross I omega, is equal to the external moments, and all of these are written in the B coordinate system. Okay, that is the important part. The Euler's equation is also valid if instead of about the center of mass we form the equation for a point O which is fixed in A. Okay, so we don't have to write the Euler equation about for the center of mass, but we can also write about the any other point which is fixed in A. Remember, A is the reference coordinate system, and we will use this fact very shortly. So let's look at an example. So this is an example of a 2 degree of freedom system. So basically it's a planar 2R manipulator. It is very well known in robotics. It is also a double pendulum. Basically I have drawn it this way, but if I had drawn it vertically hanging down, it would be a double pendulum. So there are 2 rotary joints, this one joint here, one other joint here, and there are 2 rigid bodies. This is one rigid body, this is another rigid body. So between the fixed ground and this first link or the first rigid body is one rotary joint, and between the first link and the second link there is another rotary joint. The gravity is acting downwards. This is the origin of the fixed coordinate system x, y, OA, 0, 0, and we have for each link the following parameters. So we can have a mass of this link, so m1. The location of the CG of the link is given by r1, and in this example we will assume that it is along the link. It need not be on the link, but for simplicity and simple calculations we say this is r1. We also have the z component of this inertia, which is I1. Okay, remember this is a planar motion, so Ixx and Iyy, they will not appear. Okay, I will show you that also. So the I1 and I2 are the Izz component about the CG, and R1 and R2 are the location of the CG from this OA and as well as from this fixed point here, or not fixed point, the second origin of the second link, which is here. Okay, so, and this is the end of this link, which is x comma y. The first link is rotating by theta 1 with respect to the x-axis. The theta 2 is with respect to the reference coordinate system, which is along this line. Okay, so this is a relative joint rotation. Likewise, we have a torque which is acting on this first link. So maybe there is a motor here. If it were a robot, there would be a motor here which would be rotating this link, and it would be giving a torque tau 1. Similarly, if there is a motor here, it will give you a torque tau 2. So we want to find the equation of motion for this simple, very simple planar 2R manipulator or a double pendulum. So what do? We will apply Newton's law, which is force equals mass times acceleration, and Euler's equation, which is that I into alpha plus omega cross I omega is the net external moment. Okay, and remember we are doing some matrices and vectors, so they better be all in the right coordinate system. So let's continue. Remember, as I said, it is a planar motion, so there is no z component of the acceleration. Okay, so it is only x and y component. Likewise, the angular velocity a omega b and the angular acceleration time derivative a omega b dot has only non-zero z component. Okay, it is coming out of the page, the motor axis, and that is what is giving the theta 1 dot and theta 1 double dot. Okay, so hence if you have only a omega b and a omega b dot with only z non-zero z component, then only the z component of the inertia matrix is required. Okay, because Ixx, Iyy and the terms which multiply omega x, omega y, they will go to 0 because omega x, omega y is 0. Okay, so we are only interested in the Izz into the omega z part. So for Euler equation, we need only the z component, which is I1 for link 1 and I2 for link 2. Moreover, this vector I into omega will be along omega because this is a body fixed inertia matrix with only the z component. This omega is also only the z component, so it will be like theta 1 dot. So I1 into theta 1 dot will be along omega only. Okay, because you are multiplying the angular velocity, which is along the z axis, into some scalar, which is I1. So hence omega cross I omega will be 0. So in the Euler's equation, we had I alpha plus omega cross I omega equals the net external moment. So omega cross I omega term will be 0. So let's continue. In the Newton-Euler formulation, or when we are trying to use Newton's law and Euler's equation, we have to draw what is called as a free body diagram. Okay, and what is a free body diagram? We just take a look at each link at a time. So this is link 1. So when you draw the free body diagram, you are basically breaking the link or removing this joint. So if you look at this joint, what is happening is there will be some reaction forces from the ground. So there is an F1x and an F1y. Okay. Likewise, when you break the second link away from the first link or remove the second link from the first link, we have to say that there is a reaction force or a force coming from the second link onto the first link. So this is F2x and F2y. So these directions are chosen randomly. You could have chosen in some other way. So F2y is this way and F2x is this way. It could have been the other way around, but doesn't matter. It will get automatically adjusted, because we'll see for the second link when we draw the free body diagram, we will have to also assign a force F2y and an F2x equal and opposite in the opposite direction. Okay. This is as far as forces is concerned. If you have a motor at this joint, then the motor is applying a torque to the second link. So there will be a reaction torque equal and opposite in the opposite direction. So if you go back and see the previous slide, there is a clockwise torque tau2 which is acting on the second link. So sorry, anti-clockwise torque which is acting on the second link. Hence, there is a clockwise torque tau2 which is acting on the first link. Okay. So this is equal and opposite to the torque which is acting on the second link. Now we can apply Euler's equation about a fixed point OA. Remember, Euler's equation can be applied either about the CG or about a fixed point. So in this case, it is smarter to apply about OA, because if you apply the moments or Euler's equation about this fixed point, the effect of F1x and F1y will not show up, because there is no moment about these forces. We have to worry about what is F2x and F2y. Okay. So what does Euler's equation about fixed point OA tells me? That I1 theta 1 double dot about OA. So now we have to find the inertia about OA is equal to the external moment which is acting about OA. And what is MOA? So this is tau 1 which is acting. There is a tau 2 which is in the opposite direction. So it is tau 1 minus tau 2. And then we have this moment due to this force which is acting at the CG. So this is M1G. Gravity is acting this way. So hence we have minus M1G R1C1. So remember, this is the moment arm this way. And this is minus F2y L1C1, because F2y is also acting this way, and this distance is L1. This is cos theta 1. So this is the moment arm. So we have these two terms minus because they are clockwise. Okay, whereas this tau 1 is anti-clockwise. So we are assuming anti-clockwise is positive like anywhere else. And then we have this F2x into this moment arm. And what is this moment arm? This is L1 into sine of theta 1. The vertical distance is sine theta 1. So the external moment is tau 1 minus tau 2, then minus M1G R1C1 minus F2y L1C1 plus F2x L1S1, where F2x and F2y are reaction forces on link 1 due to link 2. Next, we draw the free body diagram of the second link. So what do we have here? We have F2x. Remember, F2x was acting in the opposite direction for link 1. So here it is acting in the x direction, and F2y is in the y direction. The gravity is a force which is M2G, which is acting at the CG. So for rigid body 2, we can apply Newton's law, which is M2 into AC2 is equal to F, the net external force. And we can also apply the Euler's equation about the CG. Now in this case we don't have any fixed point, but we can apply Euler's equation about the CG, which is that I about the CG into alpha, which is omega 2 dot, plus omega cross I omega 2 will be equal to external moment m. Now this is 0, because why? Because omega 2 is coming out of the page. IC into omega 2 and omega 2, they are in the same direction. So something like two vectors, cross product of two vectors which are in the same direction is 0. Right? So this is a planar motion. So IC omega 2 is along omega 2. So we can use Newton's equation, we can use Euler's equation. So why did we not use Newton's equation earlier? Because we were taking the Euler's equation about the fixed point, and there is no motion of that fixed point. That doesn't have any acceleration. So for rigid body 1, the inertia matrix about OA is nothing but I1, which is the inertia matrix about the CG plus M1R1 square. So this is parallel axis theorem. And then we can rewrite that equation, the Euler's equation, as I1 plus M1R1 square into theta 1 double dot is right hand side remains same, tau 1 minus tau 2 minus M1G R1 C1 minus F2Y L1 C1 plus F2X L1 S1. Okay, so these reactions F2X and F2Y we don't know. So we need to somehow get rid of them. They need to be eliminated, and that can be done by considering rigid body 2. So we know that from Newton's law, m2 into ac2x, so which is nothing but the x component of the acceleration vector, is F2x, which is the x component of the force which is acting on the second link. Similarly, m2 into ac2y is F2y minus mg. Remember, there is a force in the negative y direction, which is the weight of the second link. And we also have the Euler's equation for the second link, which is I2 into theta 1 double dot plus theta 2 double dot. Remember, theta 2 is relative to theta 1. So the angular velocity and the acceleration will be theta 1 dot plus theta 2 dot and theta 1 double dot plus theta 2 double dot respectively. That will be equal to tau 2, which is the torque acting, and the moment arms, which are R2 S1 to F2x plus R2 C1 to F2y. Okay, so from these two equations 2 and 3, okay, if I know what is AC2x and AC2y, so the x and y component of the acceleration of the center of mass of the second link, I can find out what is F2x and F2y. Then I can substitute F2x and F2y in this equation, and also I can substitute tau 2 in this equation, and then we can simplify and get rid of F2x and F2y. Okay, so we can eliminate F2x and F2y if I know what is the x and y component of the acceleration of the center of mass of the second link. So let's continue. So for the rigid body 2, we know that the angular velocity is nothing but 0, 0, theta 1 dot plus theta 2 dot. This is obvious. How about W angular acceleration? It is 0, 0, theta 1 double dot plus theta 2 double dot. It's a vector along the, both are vectors along the z axis. The position vector of the second link, the CG of the second link, is L1 C1 plus R2 C1 2, and the y component is L1 S1 plus R2 S1 2. So it is nothing but simple vector. So you go from the origin OA to the end of the first link, and then again you go from there by R2 to the CG of the second link. The velocity of this center of mass of the second link is nothing but the time derivative of this. So we use chain rule. So derivative of L1 C1 is minus L1 S1 theta 1 dot, and the derivative of this is minus R2 S1 2 theta 1 dot plus theta 2 dot. Okay, so the y component will have L1 C1 theta 1 dot and R2 C1 2 theta 1 dot plus theta 2 dot. How about acceleration? We can take the derivative of this velocity of the center of mass, and these are the x and y component of the acceleration of the center of mass. So this is shown next. So let us continue. So for rigid body 2, we find that the acceleration of the center of mass is the derivative of the velocity vector So the velocity vector had two terms. So now when you take the derivative and use chain rule, you will have four terms. So the x component, for example, is minus L1 S1 theta 1 double dot minus L1 C1 theta 1 dot square minus R2 S1 2 theta 1 double dot plus theta 2 double dot minus R2 C1 2 theta 1 dot plus theta 2 dot whole square. So S1 means sine theta 1, C1 means cos theta 1, S12 means sine of theta 1 plus theta 2, and C12 means cos of theta 1 plus theta 2. The y component will have L1 C1 theta 1 double dot minus L1 S1 theta 1 dot square plus R2 C12 theta 1 double dot plus theta 2 double dot minus R2 S12 theta 1 dot plus theta 2 dot whole square. So once we have the acceleration of the center of mass of the second link, F2x is nothing but m2 into the x component. So we have m2 L1 S1 theta 1 double dot minus m2 L1 C1 theta 1 dot square and so on. How about F2y? That is m2 into the y component of the acceleration plus m2g, because there is a weight also acting. So we can find expressions for F2x and F2y once we know what is the acceleration of the center of mass of the second link. Okay, so next from the Euler's equation, we can show that tau 2 is nothing but I2 into theta 1 double dot plus theta 2 double dot plus m2 L1 R2 C2 theta 1 double dot plus m2 L1 R2 S2 theta 1 dot square plus m2 R2 square into theta 1 double dot plus theta 2 double dot, and we also have this gravity term which is m2g R2 C12. So what is the next step? We substitute F2x and F2y which we obtained in the previous slide and tau 2 which is here in equation 1 for the rigid body 1. So if you substitute, okay, so what we can show that you will get some term which is I1 plus m1 r1 square into theta 1 double dot plus I2 plus m2 r2 square into theta 1 double dot, and then we have this previous terms F2y and F2x and so on. So we will substitute F2x and F2y and simplify. So F2x is a long term, remember it is m2 into AC2x, and F2y is m2 into AC2y plus mg. Okay, so this becomes very long, that's why I have not yet fully substituted, but you can do it. You can substitute and then simplify. So once we substitute F2x and F2y, which were nothing but m2 into AC2x, and F2y was m2 into AC2y plus mg, and then simplify everything together, we will get these two equations of motion. Okay, let's go over it term by term. So tau 1 is the torque which is acting on link 1. Okay, and it is given in terms of I1, I2, m1 r1 square, m2 r2 square, and then two other terms which are m2 L1 square plus 2 m2 L1 R2 C2 into theta 1 double dot. So what is I1? I1 is the z component of the moment of inertia of link 1 about the CG. I2 is the z component of the moment of inertia of link 2 about the CG. So this is I1 is IZZ1, I2 is IZZ2. M1 R1 square is nothing but I1 plus M1 R1 square is like parallel axis theorem. So we find the moment of inertia about the fixed point OA. Likewise for I2 and M2 R2 square. And this M2 L1 square is because the second link is at a distance L1. Interesting term is this one. So this is 2m2 L1 R2 C2. So this is something like an equivalent moment of inertia as seen by joint 1. So this is theta 1 double dot is like omega dot or alpha. But there is a term in the inertia which is multiplying theta 1 dot, which is the function of the second rotation angle theta 2. C2 is theta 2. Likewise, we can have another term which is multiplying theta 2 double dot, which is I2 plus M2 R2 square plus M2 L1 R2 C2. So again we can see one term which is a function of theta 2. Then we have this Coriolis and centripetal type of term, which is M2 L1 R2 S2 2 theta 1 dot plus theta 2 dot into whole theta 2 dot. So this is like theta 2 dot square, and this is like 2 theta 1 dot theta 2 dot. Okay, so theta 2 dot is like centripetal, and 2 theta 1 dot theta 2 dot is like Coriolis. And then we have this effect of gravity. So the gravity comes in two terms, which is M2G L1 C1 plus R2 C12 plus M1G R1 C1. The second equation of motion is tau 2, which is the torque given by second motor on the second link. Okay, so that is given by I2 plus M2 R2 square plus M2 L1 R2 C2 into theta 1 double dot plus I2 plus M2 R2 square into theta 2 double dot plus M2 L1 R2 S2 theta 1 dot square plus M2 G R2 C12. Okay, C12 stands for cos theta 1 plus theta 2. So as you can see, there are many terms. Okay, and we have to be very careful while doing this substitution and simplification. At the end of this module, I will show you one way of getting error-free equations of motion using computer tools. But for the moment, let's assume that this has been done by hand carefully, and we get these two equations of motion, which are second order because it second derivatives theta 1 double dot theta 2 double dot is there, and there are two of these. So let's continue. So we can reorganize those two equations of motion as in this form. Okay, so we have tau 1 and tau 2, which are the external torques given by these two motors. One matrix, which I'm going to call as M of theta 2. Note it's only a function of theta 2, because remember in the terms multiplying theta 1 double dot and theta 2 double dot, some cos theta 2 was there. Theta 1 was not there. And then we have this vector which is minus M2 L1 R2 S2 theta 2 dot into 2 theta 1 dot plus theta 2 dot, and the y component or the second component is M2 L1 R2 S2 theta 1 dot square. Okay, and similarly we have a gravity term which is M2 G L1 R C1 plus R2 C12 plus M1 G R1 C1, and this other for the second equation it is M2 G R2 C12. So it turns out, and you can see carefully, that this matrix, which is also called the mass matrix, is always symmetric. Okay, which means M12 is same as M21. This is a 2 by 2 matrix, so this is a 2 by 1 vector. Okay, so hence this one is a 2 by 1 vector. So we have this as a 2 by 2 matrix. Okay, and then this is a symmetric matrix. So these two terms are the Coriolis and the centripetal term, because theta 2 dot square is sort of like the centripetal term, and theta 1 dot theta 2 dot is like the Coriolis term. So this is a Coriolis term, theta 1 dot square. And these two terms here, the two M2G and M1G, you can see that they don't contain theta dots or theta double dots. They are only functions of theta 1 and theta 2, which is the configuration of this 2 degree of freedom system, this planar 2R manipulator. In this lecture, we revisited the concept of mass and inertia of a rigid body. I introduced the Newton's law and Euler's equation of motion for a rigid body. I showed you two examples of application of Newton's law and Euler's equation. The first example was that of a mass subjected to a force acting along the x direction, and we saw what happens to the motion of the mass. The second example was a little bit more complicated. It was a planar 2-hour chain or a double pendulum, and I showed you how using basic mechanics and the concept of free body diagram we could derive the equations of motion. In the next lecture, an algorithmic form of the Newton-Euler's equation called the Newton-Euler formulation for serial chains will be discussed.